Hello everyone, so in this video we're going to pick up where we left off in section 13.1 and we're actually looking at subsection 2 here, which is the graph of functions of two variables. Right? So the graph of a function of two variables is the set of all points x, y, and z for which z is equal to f of xy and xy is in the domain of f. This graph can be interpreted geometrically as a surface in space. So again, we used the analogy before. When I looked at a function of one variable, y equals f of x, I had this x value and then I plugged it in and I got an f of x value or an a y value, right? So now what's happening that when I have a function of more than one variable, right? So for example, if I have a function of two variables, I plug in x and y and I get a z value. So I have this x and I have this y that I plug in, and then I get an f of x, y value or a z value that will be my third component, right? So that's why this is 3 dimensions and it can be interpreted as a surface in space. So I plug in an x and y point, I get a z point, which will correspond to the x, y, and z components of a surface in space. Okay, so let's look at example 2 here. Consider the function given by f of xy equal to 16 minus 4x squared minus y squared. And first we want to find the domain and range, and after that we want to describe what the graph looks like, right? So part A, if I want to find the domain, same thing that we looked at in the last video, right? I would need to have whatever's underneath the square root, which is 16 minus 4x squared minus y squared. I need that to be greater than or equal to 0, because then I will not plug in negative numbers underneath the square root. So solving this, I would get 16 is greater than or equal to 4x squared plus y squared. And that's not a sphere, right? We've got to do more work. And if I divide by 16, then I'm getting 1 is greater than or equal to x squared over 4 plus y squared over 16. Right? And this is going to be easier for us to interpret, because recall that x squared over 4 plus y squared over 16 equals to 1 is an ellipse centered at the origin, right? And we could go into details about whether it's a vertical ellipse or a horizontal ellipse. In this case, it's going to be a vertical ellipse. In other words, it would look something like that, right? And it would be longer than it is wide, right? So that's the idea here. How do I know that? Because the value underneath the y is bigger, right? But it's an ellipse. And so if I were going to write my domain would be all points x and y that lie, or I should say, we'll just say lying on or inside, right? Because I have a equal to sign, and inside because it's less than or equal to. So on or inside the ellipse given by x squared over 4 plus y squared over 16 equals to 1, right? And so if I'm going to write that out, I would look like x squared, it would look like the set of all points x and y such that x squared over 4 plus y squared over 16 is less than or equal to 1. So now let's talk about the range. We haven't talked about range yet, but range in this case would start to look like, in the case of an x and y, a function of one variable, the range was the y values, right? Now it's a function of two variables, so my range is going to be the z, right? It's going to be what possible output values could I have. Well, if I look at this guy here, this is my z, right? And so if I were going to find my range, the biggest that z could be, well, I'll write z equals f of xy, is, well, if I look at this here, if I'm subtracting things, right? 16 is my big number here, and I subtract things to make it smaller. If I subtract too much, it becomes negative, and it's no longer a point that's in my domain, which means it's no longer a point that gives me a value in my range, right? So if x and y are negative, is the same as if they're positive because I'm squaring x and y. So in this case, the biggest value that my z can be, or my f of x, y could be, would be 16, and that would correspond to when I have x and y equal to 0, right? Any other value I plug in for x and y will give me a number smaller than 16 because I'm subtracting it from 16 and then taking the square root, right? And so I should apologize. The biggest my z could be would be the square root of 16. So the biggest that z equals f of x, y could be is the square root of 16, which is 4. The smallest that z equals f of x, y could be is 0, right? Because I could have, off the top of my head, I can't think of what the value would be, but I could have, well, actually, if I had the value to 0, right, that would give me 0, right? I couldn't have anything smaller than 0 because this whole thing, this output, is a square root, and square roots have to be greater than or equal to 0. Right? You can't take the square root of a number and get negative. Right? So what does that mean? That means that the range here is going to be 0 less than or equal to z, because the smallest it could be would be 0, and then the largest it could be would be 4. So that is my range. Right? So now B, we want to describe what the graph looks like, right? So a point on z equals 2, or I'll just say a point, we'll call it a three-dimensional point. So a point x, y, and z is on the graph of f of x, y, if and only if z is equal to, when I take the square root of 16 minus 4x squared minus y squared, right? So if I have three numbers here, say this is my random number that I plug in x, this is my random number that I plug in y. If when I plug in that x and y value, I get this specific z value, then I know it's a point on the graph, right? And so I know this equation holds, right? So now let's solve this. I end up getting z squared is equal to 16 minus 4x squared minus y squared. So this would give me, if I brought everything to the other side, 4x squared plus y squared plus z squared equals 16. And if I want to interpret this as a surface in space, remember we always like to have 1 on the other side of the equal sign. So I'd get x squared over 4 plus y squared over 16 plus z squared over 16 equals to 1. Now what is this? And remember, what were my possible y values? My possible y value, or not y values, I'm used to saying y. What are my possible z values, or my range values? Remember that was z was between 0 and 4, right? So what this looks like, what is this shape right here? This is an ellipse, or ellipsoid, right? Because it's three-dimensional. So this is an ellipsoid, but only these z values are allowed, right? So if these z values are only allowed, so I'll say an ellipsoid, we'll say centered at the origin. How do I know that? Because I don't have x minus something, y minus something, and z minus something. So it's an ellipsoid centered at the origin, but only the top half, right? Because I don't want negative z values. If it was centered at the origin, it would have some spots underneath the xy plane and some above the xy plane, but we only want those parts above the xy plane that have positive z values, right? So if I were going to draw that, it would look like this, right? So this is my xy plane. Notice that if I were going to look right in here, this is my ellipse, right? This shape right here is my x squared over 4 plus y squared over 16 is equal to 1, right? That's my ellipse. That's my domain, my allowable x and y values, right? Everybody that lies inside of that or on that is my domain, right? And then the whole shape that's colored in there that's blue is my range, right? So all that's colored in there is my range, and it creates this three-dimensional surface, which is an ellipsoid, the upper half of an ellipsoid. Okay, so obviously drawing three-dimensional shapes is challenging. So one way to do that is to look at level curves, right? So second way to visualize a function of two variables is to use a scalar field in which the scalar, which is z equals f of xy, is assigned to the point xy. So a scalar field can be characterized by level fields or contour lines along which a value of f of xy is constant, right? So the first two examples here, the first two pictures, this picture and this picture, are two examples of level curves that you may be familiar with or seen before. Like in this case, the first picture, it shows the lines show equal pressure. So everybody that's on this line here all has the equal pressure of 1,000 isobars, right? Or measured in millibars, right? 1,000 millibars, right? And everybody that lies on, see, this line all have the same equal pressure measured in millibars. And then there's another one here that's degrees, so this one makes a little bit more sense, right? So everybody that lies on this line here all has the same temperature. Everybody that lies on this line here all have the same temperature, right? And another way, and I guess for me, the way I think about it more often is with the way I've seen this most frequently is topological maps where they show like the height of something, right? So contour maps are commonly used to show the regions on the Earth's surface with level curves representing the height above sea level, right? And this is called a topological or topographic map, right? So right here, this is showing some part of the world, and I know that right here, because it's really, really dark and lines are really close together, I know that it's really, really steep, right? And then I know this is the top of the mountain. Oops. And down here, I know that this is lower. Down here, I know that this is lower. I know it's pretty steep right here. It's pretty steep right there. How do I know all this information? Well, because a lot of space between level curves means that it's changing slowly, and little space between level curves means it's changing rapidly, right? So again, that's the idea of this right here, because all those lines, those level curves are very close. We know it's really steep, right? So again, you're probably familiar with that when you took like a geography class or something in your youth. But we're bringing that back now, and we're bringing that back with this idea back with our curves that we're used to. Right? Okay, so to produce a good three-dimensional illusion on a contour map, it's important to choose C values that are spaced evenly. My C values are going to be my contour lines, right? So example 3, the hemisphere, and I probably should cover this up here, so let me right? So if I were going to, I have this hemisphere that looks like 64 minus x squared minus y squared underneath the square root. It's shown below, right? So that's this hemisphere. And we want to sketch a contour map of this surface, right? So if I were just going to like sketch it, really without doing any work, I know that right around the edges right here, it's going to be really, really tight, and then it's going to space out a lot less as we go up the center, right? Because it's really steep right here on the edge, but up here it's not very steep, right? So I kind of have an idea that this is what my curve, my contour map is going to look like, but let's show how we do that, right? So I want to show a contour map using curves corresponding to c equals to 0, 1, 2, and through all the way through 8, right? So for each value of c, remember c is equal to some z value, and it's all those guys, everybody that has that same z value, right, or that same output. So I want to draw a line corresponding to all the x and y points that have the same z value, right? So for each value of c, the equation f of xy equals to c is going to be a circle, right? Because if I were going to set this equal to c, I'd square c, and then I'd pull the x squared and the y squared to the other side. So we'll show how to do that, but off the top of my head, I know this is going to be a circle in the xy plane. Right? So I know that when I draw these level curves, again, when I just made that sketch, I already kind of knew that that was what was going to happen. Remember, I said, okay, well, if I were going to draw this, it looks like circle, a bunch of little circles really tight, and then less tight circles that are farther apart. How did I know that they were going to be circles? Well, because this looks like a hemisphere, but looking at the equation, I also know that it's going to be a circle. So let's let's figure out what my circle would be, or my first contour line corresponding to c equals to, c equals to 0. All right, so if I did c equals to 0, then what do I get? I get 0 for my y, or for my z value, and then I get the square root of 64 minus x squared minus y squared. So I'd get 0 squared, which is 0, is equal to 64 minus x squared minus y squared, which means I get x squared plus y squared is equal to 64. And what is that shape? That shape is a circle of radius 8, right? And it's centered at the origin, right? So that would be the first the first contour line that I draw. Right? And fortunately for us, we have this nice picture, because when we draw it, it would probably be a little bit brutal. So if you look here, for c equals to 0, this is what my curve should look like, which is a circle of radius 8. And if you notice, for c1 equals to 0, or when c is equal to 0, that's that farthest outside circle, right? So that would be like this guy right here, and that is a circle of radius 8. I'm not going to go all the way around because I'd probably butcher it, but that is there. So now let's do another line for another level curve for c is equal to 1. So I get 1 is equal to the square root of 64 minus x squared minus y squared. 1 squared is 1, so 1 equals 64 minus x squared minus y squared. Solving this, I get x squared plus y squared is equal to radical 63. Or I'm sorry, is equal to 63. Now, what is this shape? This is a circle with radius radical 63, which if I plug into my calculator gives me 7.94, right? Which is really close to 8. And that was what we were expecting, because we wanted it to be really close. We assumed that it would be really close, because we knew that it was increasing really close to the edge here. Our slope, or going up, that was very rapid, right? It's very steep right there. So for c equals to 1, right? If you look at that, that is they don't even have a line for it, because it's just so close to c equals to 0, right? But we could probably just draw it in there really close to c equals to 0, right? It's this circle that's very, very close, and that's why the outside line looks really, really dark. It's just because the other line is so close to it, right? So let's do one more here. Let's just say like dot, dot, dot. Now, what's the next one here? Let's maybe do corresponding to C7, c equals 7, right? So c equals 7, we want 7 is equal to the square root of 64 minus x squared minus y squared. So So I get 49 is equal to 64 minus x squared minus y squared. So I get x squared minus y, or plus y squared, is equal to 64 minus 49, which is equal to 15. And so we know that this is a circle with radius radical 15, which we know is going to be less than 4. Radical 15 is 3.87. All right, so this is a circle of radius 3.87. So let's draw this one here. For C7, it's a circle with radius almost 4, so a little bit less than. If you notice, when I look at C equals to 7, that is going to be this circle right here, because it has a radius of a little bit less than, I'll just draw right there. It has a circle of a little bit less, or radius of a little bit less than 4, right? So that's how this works. If I were going to draw a contour map, I just choose a bunch of different z values, and those z values will correspond to some, I choose a bunch of c values, which correspond to the z values, or the outputs on the map. I figure out which x and y values give me that output, and then I draw the line corresponding. So in this case, these x and y values that correspond to a circle of radius 8 give the output of 0. All right, and then if I have these x and y values that are on this circle give an output of 1. These x and y values that are on this circle give an output of 7, right? And that's how this works. And then I end up seeing the shape, and you can kind of visually, just by looking at my contour map, I can see that it's really steep on the edges and not as so steep right at the top, right at the peak, right? Which corresponds exactly to this hemisphere up here. All right, that's all I have for this video. Thank you.